I'm Adam from RFOXiA from our real lab. Today we're answering why does a GPS product that works perfectly in one country degrade or lose fix entirely when deployed somewhere else, and what the correct hardware solution actually looks like. Enjoy our new soundtrack at the end of the video. Let me start with something most developers have never been told because the GPS marketing materials do not mention it. GPS accuracy is not a fixed number. The 1.5 meter figure you see on a datasheet is a best case measurement. What you actually get depends on how many satellites your receiver can see at any moment and where those satellites are positioned in the sky above you. This is called satellite geometry, and it is not the same everywhere on Earth. GPS satellites orbit at roughly 20,200 kilometers altitude in 6 orbital planes with about 31 active satellites in the constellation. That sounds like a lot. In practice, from any fixed point on the ground at any given moment, your receiver can see somewhere between 4 and 12 of them. The positioning accuracy your module delivers depends entirely on how those visible satellites are distributed across the sky. If they are clustered together in one quadrant, which happens regularly depending on your location and time of day, your vertical accuracy degrades significantly. This effect is measured as dilution of precision, or DOP. Low DOP means good geometry. High DOP means your fix is degraded, and GPS-only devices have no way to compensate for it because they have no other satellites to draw from. Now here is where geography enters the problem. GPS was designed and calibrated primarily for use in the United States. The ground control stations are mostly located in the continental US and US territories. The constellation coverage is optimized for mid-latitude North America. This does not mean GPS does not work elsewhere. It means that at certain latitudes, certain times of day, and certain geographic regions, the satellite geometry for GPS specifically is worse than what you measured in your lab in New Jersey. A device shipped to northern Scandinavia or southern Australia or anywhere near the equatorial band is operating with a different constellation geometry than the one you validated against. GLONASS is the Russian constellation. It has 24 satellites in 3 orbital planes. Its inclination angle is slightly higher than GPS, meaning it provides better coverage at high northern latitudes, Siberia, Scandinavia, northern Canada, than GPS does alone. Galileo is the European constellation, also 24 satellites, similar coverage to GPS with better performance in Europe and regions where EU ground stations provide differential correction. Beidou is the Chinese constellation, over 45 satellites optimized heavily for the Asia-Pacific region and the fastest growing constellation in terms of active satellite count. By 2024, it had more active satellites than GPS. When you support all 4 constellations simultaneously, your receiver has access to over 100 potential satellites. In practice, it sees 20 to 40 of them at any moment, depending on location. More visible satellites means better geometric diversity, lower DOP, and more consistent accuracy. More importantly, it means that if GPS geometry is poor at your user's latitude and time of day, GLONASS or Galileo satellites fill in the angular gaps. The fix rate stays high, the accuracy stays consistent. The user in Japan and the user in Brazil get the same product experience as the user in your lab. Here is the failure mode that no one talks about when they ship GPS-only products. It is not a crash. It is not an error message. The device keeps running. It reports a location. It reports an accuracy estimate. But that estimate is wrong because the DOP is high and the receiver has no way to compensate. The product appears to work. The data it produces is subtly degraded. For most consumer applications, this is invisible. For a drone navigating autonomously or a precision agriculture system or a survey-grade mapping application, this silent degradation is the entire problem. You cannot reproduce it in the lab because your lab is not in Hokkaido. The fix rate problem is more obvious but still frequently misattributed. At 18 Hz, the Multinav Pro Plus is delivering a new position solution 18 times per second. For that to be consistent, the receiver needs to maintain lock on enough satellites to continuously solve the position equation. If you are GPS only and you enter a region with poor satellite geometry, you may drop below the minimum satellite count to maintain a valid fix. The receiver reports no fix. Developers blame interference, firmware bugs, antenna placement, everything except the actual cause, which is that the constellation they chose does not have adequate coverage at that latitude at that time. The solution is not complicated, it is just expensive to do correctly in hardware. You need a receiver chip that can simultaneously track multiple constellations without switching between them, and you need an antenna and RF front end designed to receive the full frequency range those constellations operate on. GPS L1 is 1575.42 MHz. GLONASS FDMA signals span 1598 to 1606 MHz. Galileo E1, so that is the geometry problem. 4 constellations, 1 fix, consistent accuracy everywhere on Earth. Now let me show you the actual module that does this. This is the Multinav Pro Plus built around the u-blox MIA-M10Q. That chip is what makes concurrent 4-constellation reception possible. GPS, Galileo, GLONASS, and Beidou tracked simultaneously, not sequentially. The result is consistent fixed quality regardless of where your product is deployed, not just where you tested it. Less than 1.5 meters accuracy and an 18 Hz fix rate. The fix rate matters as much as the accuracy number. At 18 Hz, the receiver is solving position 18 times per second. When multi-constellation geometry keeps satellite count high, that rate stays consistent. With GPS alone in a poor geometry region, it does not. The module runs at 25 to 30 milliamps and measures 26 by 22 millimeters. For a module doing concurrent 4-constellation tracking, that power draw is extremely controlled. The compact footprint means it integrates into drone flight controllers, portable trackers, and wearables without occupying board real estate you do not have. UART and I 2C interfaces with 1.8V and 3.3V voltage support. This is deliberate. Most embedded development targets one or the other, and some targets both. The Multinav Pro Plus connects to whatever your microcontroller is already using without a level shifter or additional circuitry to worry about. The open source C library includes full NMEA protocol support. This means your existing GPS parsing code works without modification. NMEA sentences from a 4-constellation receiver look identical to NMEA sentences from a GPS-only receiver. The parser does not care, and you do not have to rewrite anything to gain the global coverage improvement. uCenter lets you visualize exactly which satellites the module is tracking and from which constellations. When you are validating deployment in a new region, this is how you verify that Galileo or Beidou satellites are filling in the geometry gaps that GPS leaves. You can see the DOP value improve in real time as the constellation count increases. Drones, IoT sensors, wearables, automotive tracking, research platforms, anything that needs to work reliably in more than one country. If your product ships to users across multiple regions and you are building on GPS-only hardware, you are shipping a product that will perform differently depending on where the user happens to be standing. 1575.42 MHz. Beidou B1 is 1561.098 MHz. A truly concurrent multi-constellation receiver is tracking all of these simultaneously, correlating satellite signals in parallel and fusing the position solutions. That is what the u-blox MIA-M10Q does, and that is why the Multinav Pro Plus delivers consistent 1.5 meter accuracy and 18 Hz fix rate, regardless of where on the planet it is deployed.
Constellations up above, locked in orbit, signal love. 18 fixes every second, every meter calculated. No drift, no guess, no hesitation, just the truth of your location. 1.5 meters from the truth, every coordinate living proof. GPS, Galileo, GLONASS aligned. Beidou locked exactly where I am. Precision at the speed of land. Fast moving platform, still it holds. Signal strength that never folds. Sky above becomes a map. Every second fills the gap. Urban canyon, open field. 4 constellations never yield. The sky is full of signals. waiting to be heard. Every satellite a compass, every fix confirmed. Nowhere on this planet falls outside the grid. 0.5 meters margin, that is all there is. 1.5 meters from the truth, beat locked exactly where I am. Precision